Hello there, welcome to Codebase Alpha. This is episode 47 and it's an unusual streaming time for me on a Tuesday, and I'm not expecting to have many people in chat today because I'm up against the big hitters. Dev Chatter's streaming. I know Gareth Hubble is streaming later as well, so I'm expecting chat to be pretty quiet. But I did want to stream because I did want to try to move our projects forward and to to keep things going really. So let's go over to the code and see what we need to do next with our plugins. So let's just pop over here. So here's our Codebase Alpha FX header file, where last time we kind of defined a couple of classes, a simple delay effect, alpha simple delay, and this contains all of the the logic, the signal processing logic that we need to get a simple delay effect. So we processed all that and tested that, and then we created another class, which is the alpha chorus class here, and this produces the chorus effect. So this is like multiple echoes. It's like multiple people playing the instrument or singing or whatever. So it's like that choir effect. And can be quite powerful and quite disorientating if the parameters are tweaked up quite high. So we did play with that a bit last time. So we can try that out as well. I can show you that. But one of the things that we get kind of almost for free with the chorus plugin is flanging as well. So flanging is a much more subtle effect in many ways. It was originally created using two tape decks, so the tape decks would play the same kind of track, and but someone would perhaps put a weight on one of the reels of one of the tape decks, or maybe run their thumb along the side of one of the reels to slow it down very, very slightly. And what would happen is that the music or the kind of the signals from the tape decks would kind of come in and out of phase and produce this flanging effect. And it's quite hard to describe what a flanging effect is, but we'll actually give it a go and try and create one. It's fairly simple to do. What we're going to have to do though is be able to switch between having a chorus effect and having a flanging effect. So we're going to need to have a new parameter. We've got these four parameters here. We've got our wet dry mix, so wet being the processed samples and dry being the unprocessed samples. We've got a feedback gain, a rate of our low frequency oscillators to oscillate, and a depth, the kind of range over which they operate. So we're going to need to have a type. So it's going to be chorus or flange. So let's create an enum. So enum class chorus type, and we'll set that to either be and we'll use this convention of putting K in front of them, I think. So this is going to be K chorus or K flanger. And that should be what we need. There. So we're going to need to add another parameter here, which is going to be our type. So if we go down to our private variables, which are down here, we can set chorus type and we'll set it by default to be K chorus. Now I think perhaps I'm not sure about whether we should have capital C in this case. If I was working with C++, it would be capitalized, but perhaps not in this case. And this is going to be that, I think, is it chorus type? Type name not allowed, so why doesn't it? Okay, so I don't know, obviously I'm missing something about Have I misspelt it? Is it as simple as that? Okay, chorus. Okay, well let's have a look at the code that's in our FX objects. That's in our our JUCE modules. FX objects is the fxobjects.h file. So this is what we're modeling our code on, really. So this is the package which I got from the book I'm using, which is Will Perkel's book, Designing Audio Effects in C++. And we should have some enums in here. So as you probably gather, I'm learning C++ as well as learning DSP and the JUCE framework. So here we have enum class, and then we have a name, and so it's just, oh, it's a double colon, of course. So I should have known that, shouldn't I? I should have known that. So let's set it up. So it's going to be chorus, not dot, but double colon. There we go. So we set our default chorus type to be a chorus. Let's go and make that available to us here as so this is going to be chorus type as well. Chorus type, and that's going to be type, and that's also going to be set to chorus type. Okay, chorus as a default there. And we're going to, and we're also going to have it passed in as a parameter. So type is going to equal parameters dot type there. Okay, so let's make sure I set that the same. I called it type here. Okay. So what else do we need to do? Well, when we're working with a flanger, the basic differences between a chorus and a flanger are that a flanger uses a sine wave and a chorus uses a triangle wave. So you can see down here we're setting our LFO to be a triangle wave. We also instead of going from -1 to +1, we want the value of our LFO to produce 0 to 1. It's called a unipolar wave. So a unipolar modulation, when it's going from -1 to +1, that's a bipolar modulation because it has negative and positive sides. With a flanger, we want it to go from 0 to 1, and also these values here, which are the delay offsets, are going to be much smaller for flanging. So let's look at what we need to do to change this. So we can pass the type of effect we want in on the parameter struct, which is up here, which is this alpha chorus parameters, and down here we do a reset and we update the LFO parameters. Okay, so if we update the LFO parameters, if we go to that, then we're going to need to pass in the chorus type. So in here we're going to have chorus type, type, and we're going to want to say that if type is equal to chorus K chorus, then do that. Else we must be dealing with a flanger, in which case we want the waveform to be a sine wave. So let's change that to K sine. Small k. And we want to do the same down here, so let's just the same here. Type is equal to chorus type colon K chorus. Then the right hand LFO will generate triangle waves, else we're going to have it generate sine waves. K sine. Okay, so that's the initial, that's setting the waveform. And then we've got this get delay in samples. So what happens is we need to pass in type into there. See, type's not a great name, is it really? But it's working okay. We'll leave it like that for now. Let's change it. Plugin type. Let's change it to that. And up here, plugin type is that. And same there. Okay. Right, so we need to pass in plugin type into our update parameters there and into there. Alright, so that's our LFO parameters. So remember, LFO is our low frequency oscillator, so that's what's producing our modulation. Instead of being a signal we're actually going to hear, this is an inaudible frequency anyway, but it's between, I think, 0.1 Hertz and 20 Hertz, which is outside the range of human hearing. This is actually modulating the parameters, the delay parameter. So here we're using this get delay in samples function, and we're passing in the LFO. And we're multiplying by the parameter depth. Okay. So what is the best thing to do there? Well, let's go in and let's pass into that, as well as the LFO value, let's pass in the plugin type as well. So here's let's update parameters, and here's get delay in samples. So let's pass in chorus type again, and pass it in where we use it. So that's going to be plugin type, and down here plugin type. Okay. So we're pre-multiplying by our depth parameter here, so that's okay. This is going to be currently we're going to be getting a triangle wave or a sine wave, which is oscillating at a maximum between plus and minus 1, and that's going to get fed into our get delay in samples. So we need to do things inside here. Okay, so what we're going to say is if type is equal to chorus type colon K chorus, then we're going to do that. Oops, get rid of that. There we go. We'll indent those lines there. Okay. So if that's not the case, right, we want the LFO mapped to be a unipolar signal. So do we have a bipolar to unipolar? Bipolar to unipolar, we do. So this is going to calculate the unipolar value from a bipolar value. It's exactly what we want. So we want to pass in our LFO value in there. So we're going to say our float. Is that a double? Float. What's going to come out of this? A double. So double unipolar LFO value is going to equal that. And then we're going to want to have something very similar to this. This is going to be the flanger effect delays. So here we want the unipolar value passing in, and we're going from this time from 0. Sorry, that's wrong. Yes, 0, yes, to 1. It's going to map to 0 up until 5 milliseconds. Like that. So we need to cast this into a float. Oh, it'll accept a float. That's good. LFO value should be LFO value from there. That's correct. Okay, and the sample rate then will be the LFO mapped multiplied. So the return value, which is going to be our delay in samples, is the sample rate multiplied by the value of our delay, which is either 0. It's on the continuum between 0 and 5 milliseconds. So it's a very, very short kind of delay. Okay. I mean, that should be enough. Let's make sure it builds. So cheers, everybody. Thank you. Anyone who's joined me, do speak up in chat if you are out there. I know that it's I'm up against the big hitters today, so I know I'm not going to get many viewers. So, but that's not the point of streaming, really, is it? It's what we're trying to do is to move the project forward and make sure we try to stream at least every week. As you may know, I'm on annual leave this week, which is why all the schedule's a bit messed up. Okay, so that compiled okay. Let's go over to our plugin processor, and we're going to, when we create our delay, which is, sorry, our chorus, we're doing a reset sample rate there, which is correct, and then we're updating parameters here. So what we're going to do is we're going to set chorus dot plugin type So interesting, if chorus plugin type doesn't seem to be available to me. It's inaccessible because it's not in the correct place, is it? Okay, so let's go over here. So our struct should have everything public. Plugin type. Interesting. So why is it inaccessible? Okay. Chorus params. That's it. Dot plugin type. We're going to set that equal to chorus type k flanger. Oops. K flanger. All right, let's build that. So we're going to want a kind of GUI control to be able to kind of switch that that plugin type, but we haven't got one at the moment. But because of the other work I want to do, don't want to concentrate too much on refining the GUI, because the GUI is going to change. We're going to have a lot of changes to our GUI, so I don't want to kind of finalize it. So let's run that up. So here we are with our plugin host, which is we use to test our plugin. So here we have the GUI that as it stands at the moment. Remember that with the chorus or a flanger, the delay setting has no effect whatsoever, because the delay is controlled by our low frequency oscillator, which is the rate and the depth here. And phase offset we haven't implemented yet, and we may not implement because of kind of plans I've got for other things. Okay, let's get our audio player up, and we'll open up our Relax Daily royalty-free sample. And what we can do here is we can dial these things right back. So no wet signal, rate of 0. So this should be the pure dry signal coming through, which it is. So let's feed some and you're getting a flanging effect. I don't know if you can kind of hear that. I think so it gets very disoriented, and the tuning goes way out if we have too high a rate. So these rates need to be fairly low. So there's like a 3 Hertz and a very low depth. But it's a very tiny difference in the delay. It's only between 0 and 5 milliseconds of delay that's being oscillated around there. And that's the flanging effect. So we can put some feedback in as well. And we start getting disorientation there. It gets weird. But at 50-50 feedback, let's feed some more wet and dry in there. And we start getting really strange things happening. You can also imagine that's the result of someone with their thumb against the reel of a reel-to-reel tape deck, making that change. Let's stop that. Close this off. And what we'll do is we'll put in we'll unconnect that, and we'll put in a sine wave generator, which I'll operate from my MIDI keyboard. We'll stick in those connections, connect that up to our delay. What I'll also do is bring in an oscilloscope, and we'll see what this effect has. So what we're going to do is move everything around a bit. Pop the oscilloscope in after the delay. So connect that up like that into the oscilloscope, and then into our audio output like that. Let's try and just see, you can see the whole signal path there. So we don't need our audio player. Disconnect all pins. That's going to make it a lot easier to fit in. Okay, so that's that there. Let's bring up our oscilloscope. So I'll play a note here on my keyboard. So there's a note. So what we need to do is to slow that down a bit. And we'll increase the amplitude. Okay, so you can see the flanging effect actually happening there. So if I play a note, so it's that kind of, there's a bit of amplitude modulation going on. Can you see it's making it even bigger actually? Quite complex kind of changes to the waveform. If I increase the depth, you probably can't hear the tone because maybe that's a bit better. But it's that kind of pulsing. And you can see it's no longer a pure sine wave. If I reduce this down to having no wet signal at all, we're just getting, there's a bit of a glitch there, but it's basically a sine wave. As I bring up this, start feed the flanger effect in, we start to distort our wave in all kinds of interesting ways. And that's the flanger effect visible for you. Okay, so I think that's pretty successful implementation of flanging. So that kind of completes that kind of demonstration plugin really, but we've just scratched the surface really. These algorithms that we've implemented here are really the simplest possible ones. So we've got a very, very simple delay, which basically is a single circular buffer, and we delay by anything up to 2 seconds, and we produce echoes that way. And then we've got the chorus and flanger effects, which once again, they're the simplest possible way of doing those. But what I'd like to implement is a slightly more complicated chorus effect. And this is a chorus effect which is going to be based upon an effect by Roland, the synthesizer and musical instrument manufacturer. And it's going to be a dimensions style chorus. So the dimension effect, chorus effect, is one of their kind of trademarked digital effects for their synthesizers, and we're going to try and create one of those. So let's have a look at what that looks like in terms of a block diagram. So I created a diagram of it. Here it is. Okay. And what I'll do is I'll load that into Paint so I can write on it if I need to. Okay, let's bring it into Paint. Roll dimension. Okay. So this is a stereo only effect. We've got the left hand stereo channel up here. So let's do some writing on here. So this is the left hand channel. And this is the right hand channel, right hand stereo channel. And you can see we've got two delays. We've got circular buffers here and here, just like we have it currently. We have a shared LFO. So rather than using two LFOs independently, which happen to have the same rate and depth, we're going to use a single one, which is perfectly reasonable. We could have done that before as well. But these are going to be actually, this is going to produce the normal waveform, but this is going to produce waveforms offset by a phase of 180 degrees or pi radians. So this is going to be an inverted signal. So we're going to be inverting the signal and applying that to the modulation over here. As well as mixing that in with our wet and dry proportions here into our output signal, we're also going to be taking a tap off, multiplying that tap by -1, i.e. inverting the signal, passing it through a high pass filter and then feeding that into the opposite channel. So we're going to take a tap off the delayed signal from the right hand channel, invert it, high pass filter it, and then pass it into the left hand channel. So this is going to be, apparently this produces quite a subtle effect, a transparent effect. So I've no idea what it sounds like. I've never heard a Roland Dimension chorus unit, but we're gonna try and create one. So what we need to do is we need to have the twin circular buffers here, a single LFO which produces a triangle wave, and it's going to be controlled by a rate and depth as we have with our existing chorus effect, and we're going to offset the waveforms that are produced by LFO by pi, minus pi in this case. We're going to invert it so they're out of phase. And then we're going to do this weird thing where we pass it through high pass filters and do that. So I'm going to keep that available to us so we can look at it, and we're going to try and write this as a class. So we're going to be able to copy some code, but let's just start off with a new class. So once again, we're going to do the same kind of things we did here. We're going to implement the iAudio signal processor interface, which means we have to implement at least 3 pure virtual methods, and we'll actually need a few more because it's a pure stereo plugin. We're not going to be able to implement this process audio sample, which is the mono style processing. We're going to have to implement the stereo processing, which is in the process audio frame. Okay, so let's make a start on that. So let's create a new class. So this is called alpha dimensions chorus, and we're going to implement public signal processor. Okay, so that's the basic thing we need to do. We're also going to need to have some parameters. So let's just grab the code here for our parameters. We don't need plugin type because this is purely going to be a chorus unit. So alpha dimensions chorus parameters. Okay, so let's set this up like that. So we don't need plugin type. Okay, we're going to need a couple of more parameters here. So let's go back to our diagram. We haven't got any feedback, so we don't need a feedback parameter. What we do need is a left-hand channel wet-dry mix and a right-hand channel wet-dry mix. We're going to need a high-pass frequency cutoff frequency for our HPFs. We're going to need a rate and a depth. So that's left-right mix, cutoff frequency, rate and depth. That's should be all we need. So wet-dry mix left. We don't need feedback. And then wet-dry mix right. So let's copy these down. We got our rate and our depth. Let's fix that. That's right. And then we need a cutoff frequency. So double cutoff frequency. We're going to set that to, I don't know. I really don't know what it should be. Let's say 1000 hertz. Just as a value. I really don't know what it should be. Okay, so cutoff frequency. So equals parameters. Cutoff frequency. Okay, so there's the parameters, the 5 parameters we need, and we may add some more parameters because we have the opportunity to play with this. We could actually put gain on these 2 feeds here. So what I could do is I could put a gain control here and a gain control here. So we could control how much of this this kind of crossed over signal gets through, but we'll start off not doing that and see what it sounds like, and we can experiment with different values that way. Okay, so that seems to be what we need in terms of parameters. You'll notice that as well as defining the properties here, we've overridden the assignment operator, and that's one of the requirements that we need to be able to do in order to meet the interface for a parameter struct in our FX objects kind of way of working. So what we're doing really at the moment is we're using the building blocks provided by FX objects. And if you haven't picked up what FX objects is, I've got this book. So you can see it. It's Will Perkle's Designing Audio Effects in C++, and it comes with a whole load of code, which the FX objects is part. And all I've done is built that into a JUCE user module and included it over here. So we've got access to all those things, the kind of building blocks that he has created for us. It really means that we haven't got to. We've kind of in previous streams we've created a delay and a chorus from first principles. It means we don't have to do that anymore. We can actually work with some higher level kind of constructs. So let's create our public and our private areas here. So we're going to need to implement certain methods. So we need a constructor and destructor. We need to implement reset, can process audio frame, and process audio sample. Those are the minimum things it won't compile if we don't do those very things. So let's do that to start off with. So this is now going to be the third class I've ever written. So I'm probably going to be referring to what I did before. So this is going to be that, I believe. Is that right? No colon, is there? Just the colon's the initializer list. We haven't got an initializer list. And then the destructor, which simply has the tilde in front of it. And we're not going to put any code in those. Okay. Then we need to implement reset. So this is going to be like this. This is the signature for reset. So we're overriding that method. We need to virtual bool can process audio frame, I think it was. So we're going to return true from that because that's all we can do. We can't actually do the other one. Can process audio frame, I think, is the correct signature. Can process audio frame, yes, override that. And then we've got process audio sample. We'll just copy that one down. And here we're just going to return what was passed in because we can't actually process a single sample through this method because it's a stereo feature. And then we want process audio frame. This is going to be I think it's virtual double process audio frame, and I think the parameters in there I'll just copy down. I'll copy the whole lot down because it'll be easier for us to work with. Okay. Let's copy the basic code from above as well. So that's simply dealing with if we've got no channel input and output channels or mono. And we can stick that code in. Oops, I don't think I grabbed that, did I? Here we are. This. Input can only use stereo. Can only use stereo input. Okay. So we're pretty much ready to begin. So let's go and have a look at this again. So we've got two circular buffers, an LFO, and a pair of high-pass filters. So let's create the objects that we're going to need for those. So we'll go down to our private variables. So we're going to need the parameters. So we need an example of this struct. So we call this parameters. We're going to need a couple of circular buffers. So circular buffer left delay buffer, and circular buffer right delay buffer. And these classes circular buffer, they're templates, so we need to actually say it's going to be circular buffer floating point values. So we give it angle bracket float in there. So we're going to have floating point values coming in because that we were dealing with IEEE floating point digital signals. We needed an LFO. So LFO, we're going to call it shared LFO, just so that it's obvious we only got one of them, and it's we're using the same LFO. And we need a couple of audio filters. So audio filter left high pass filter, and audio filter right high pass filter. So audio filter is one of these high level classes which are contained within FX objects. So it saves us having to write the code for a high pass filter. It's already been done for us. It can get quite complicated to do filters. There's lots of calculations go on. In fact, within this FX objects library, all the kind of coefficients that are used in a filter have been pre-calculated, so it doesn't have to do the maths. All those values are available to it. So it really kind of it saves us an awful lot of time. Although we did look at different types of filters in the very first stream. And I did say that I would actually explain at some point how a filter works, and I'll still do that at some point. But we don't want to. I don't want to do it in a mathematical way. I want to do it in where we can do it kind of almost by filling a table in of values and putting values into the filter and see what comes out of the filter. Okay, so those are the basic bits and pieces that we seem to need. Okay. So let's go back to our diagram. Right. I think we can once again use some of the code we wrote last time to help us out. So the very first thing we do is to actually update the parameters of our LFO. So let's do that. Let's create a function, a private function called, so this is going to be a void function, update LFO parameters. In there, we're going to say that shared LFO dot get parameters. So that's, we're going to say auto params equals that. So we get the parameters from the LFO, and then we've got those available to us. So params dot what we got, frequency in hertz and waveform. So the waveform is going to be triangle. So this is signal gen data dot, maybe it's not signal gen data. I thought it was signal gen data. Let's have a look. I'll generate a waveform. That's the enum we want. So one of the problems we have, obviously, when working with new frameworks, is actually working out all the different features that are available to us. So that's one of them. So this is going to be a triangle, so K triangle. colon again, don't I? So it's going to be a triangle wave, and the frequency is going to be set by our frequency parameter, our rate parameter. Remember, it's a shared LFO, so they're both. So there's only one LFO controlling both delays, both delay delay buffers. So params dot frequency in hertz is going to be equal to parameters dot rate. Okay, so that should set up our LFO. As the user changes the rate, this will be called every time we process a stereo frame, which is one sample from the left and right channels. So we can say update LFO parameters here. Okay. So what do we do next? So we take obviously some of the right hand and left hand samples and pass them into the delay. So we need to set up our circular buffer with the right size. So let's go and look at how we did that in the last episode. Okay. So in our reset function, this is where we set up everything when we start playing a new piece of music or start a new instance of the plugin. So we can copy this piece of code down, because a lot of this stuff is going to be extremely similar. So let's implement reset. Can return true. We don't need to have that, or we don't need a plugin type in there, and this is going to be shared LFO. And the primary thing about the about reset is basically taking in the sample rate. So if the piece of music which we're playing into the plugin is of varying sample rate, so if we got one piece which is a sample rate of 44.1 kilohertz, which is CD quality, and we have some kind of super high fidelity recording which we're playing in at 96 kilohertz, then we need to change some fundamental things about our plugin, and those include the sample rate for your shared LFO, but also the size of your buffers. Obviously, the more samples per second that you have, then the more the bigger your circular buffers have got to be. we've got our right and left delay buffers. We've got a couple of parameters here. We've got a sample rate and a delay buffer size, so we can add those down here. So we've got double sample rate and double delay buffer size, and we can initialize those. Just do 0.0 for that. Delay buffer size is going to be an int. Okay. And we update LFO parameters at the same time when we do a reset. Okay. So the reason we got 2 here is because I've decided that the maximum delay is going to be 2 seconds. So we're doubling our sample rate and adding 1. So for example, if the sample rate was 44.1 kilohertz, then the size of our buffer is going to be 88,201 because we're adding 1 to it. Do you want to make sure that types that we set here, yes, delay sample rate is a double. So we're going to want to have left and right delays in samples. The delay in samples is going to be the same for both, or is it? Let's think about what we need to do. So we've got our LFO is set up. We've got our circular buffer sized. Now we need to feed samples in and delay them. And then we need to take these values out, these samples out, and pass them through. Okay. So up here, we need to render our LFO output, and we can do that using this render LFO command here, this method here. This is going to be our shared LFO in this case, and we are going to have a left and right value. So let's just grab those 2 lines of code and change them. Okay, let's put them down here. So the left LFO value is going to be output. It's going to be our shared LFO, and we're going to render the output for that. So that gives us a sample, and then we multiply it by the depth, and it's the normal output. So it's just the non-inverted output. For our right LFO value, pardon me, we're going to get our shared value again. Now, should I just have? I think I'll just have LFO output here. LFO output. So we have the same value. This is going to be LFO output, and this is going to be LFO output as well. But this is going to be an inverted signal, inverted output. So remember, according to our diagram, our block diagram here, that what goes into the right channel has been phase rotated by pi, 180 degrees. So it's inverting. So if this was a phase maximum, like +1, what we feed into the right hand channel would be -1. It's like multiplying by -1 basically, which is what's happening here. Okay, so that gives us our left and right LFO values, and then up here, what we're going to do is calculate the delay in samples, and that's simply using this delay in samples method which I had before. So let's just copy that and then say get delay in samples is a new method we're going to have. So this is going to be float get delay in samples, and we're going to feed it in a float, which is our LFO value, and we simply feed that in there. Okay, that hasn't really changed. We're still using the chorus effect delay range, and we've got a bipolar variation. So remember, this is a sine wave going from +1 to -1. So when the sine wave is at -1, we're going to output 5 millisecond delay, and then we're going to gradually, as we go through the sine wave, we can reach a maximum of 1. That's going to output a maximum delay of 30 milliseconds. So that's going to be, as our LFO oscillates, we're going to be modulating the delay that's being caused by the circular buffers. We're going to modulate that, but actually what's going to happen is that when it's -1, the left hand delay will be 5 milliseconds, but at the same time the right hand delay will be 30 milliseconds, and that's what that phase offset of 180 degrees or pi radians is doing for us. So that's where we're going to get the interesting effects. I have no idea what it's going to sound like, but that should be quite interesting. So what we can say now is that left delay in samples is going to be get delay in samples, and we're going to pass in there the left LFO value, and similarly the right delay in samples is going to be the right LFO. So these should be floats. Okay, so we need to read the values at those positions. So one of the kind of basic principles we have to adhere to when we're working circular buffers is we always read before we write, because we don't want to accidentally overwrite the location we should have been reading from the circular buffer. It's unlikely to happen in many cases, but it's possible. So depends what the value of the delay is. So we always read before we write. So let's read the left and right signals out. So what did I call them up here? So I'll just call them left and right delayed samples. So we can just simply copy the same things, can't we? Just grab that. So our left and right delayed samples, we use our buffer. We use the read buffer method on there, and we get delay in samples. Now remember, delay in samples is a floating point number, and you might be wondering, A, why is it a floating point number, and how on earth do you read a circular buffer at position 3.4? Well, we need to. So that's the problem, is that obviously we're dealing here with discrete time. We're not dealing with analog time, which is continuous and it can be subdivided infinitely. We're dealing with a sample rate, which is let's say 44,100 samples per second. So if our delay works out, we want actually delay in samples is something like 1000.5, because obviously we're multiplying a sample rate by a time, and the time is anywhere between 0 and 2 seconds. Then we still need to be able to read that sample, but it's physically not in the buffer. So what we do is do something called linear interpolation, and luckily our buffers have linear interpolation built in. Last time I didn't explain linear interpolation again, but I will do this time, just in case there's someone here that doesn't know about linear interpolation. So what we'll do is I'll just grab hold of this and make it a bit bigger, and we'll see if we can explain linear interpolation very, very quickly. Okay, so let's just fill this with grey. Okay, so I'll change colours to purple. So if you imagine that we've got the buffer here, and we'll go for green, and then oops, what happened there? It disappeared. What happened to my line? Oh, very strange. Anyway, there's the green line again. So that's our buffer, and we've got entries every few. So these are the buckets within the buffer. So, for example, this one here is position 1, 2, 3, 4, etc. within our buffer. So let's say that the sample, we have a sample in position 1 which has an amplitude of that, okay, and the sample in position 2 has an amplitude or a magnitude of that, and maybe it kind of goes on, goes down, like that. So what we want, say that our calculation where we want to read, the read buffer is going to say we want to read position 1.5. Then we're going to need to figure out how to do that. So we want to read the sample value at this position here. So all we do is draw a straight line, and that's supposed to be a straight line between those 2 points, and then we interpolate. We just take the value at that point there, and that's kind of our best guess in this simple scheme of drawing a straight line between those 2 points. Then obviously if this is 0.5, this is 1.5. I have to get a tablet. It's ridiculous. 1.5, then this is the midway point, so midway between there and there. So that's linear interpolation. There's other kinds of interpolation that you can do, which are much more complicated and which are much more accurate. So you can take samples either side here and start to try and work out what kind of curve that is. So you could say fit a parabola between those two curves, those 2 points, or fit other types of curves, and you probably get a more accurate value. But this is good enough for our purposes to enable us to get the value of a sample even in between the kind of quantized time values, 1, 2, 3. So that's basically what our class is going to do for us. So what we're doing here with read buffer, we're passing in a double, which is our delay in fractional samples, and it's going to do our linear interpolation for us. So this is a really great thing, because otherwise we'd have to kind of sprinkle our class with all the code to do linear interpolation, which is pretty pointless, because it might as well be built in to the class that needs it. So it's a kind of single responsibility. Our circular buffer needs to be able to read fractional delay values, so built into there. Okay, so that's gives us our left and right delayed samples. Now we've read them, we can actually write our input. So we have our input frame and our output frame. Our input frame contains the two stereo channels, left and right. Okay, so what we can say here is we can say, if we go back up to the previous set of codes, it's easier if I show you up there. We can do that right here. Okay, so we're not going to have any feedback, so they can ignore the feedback side. We're simply going to write into our buffer the data that came in. We've already read our delay, So this is what happened so many samples ago, but we need to write our buffer. So our new data goes into the buffer. And as I say, we always read before we write. So left delay buffer, top right buffer, and we're going to put input frame, and the left hand channel goes into that left hand sample, and a right delay buffer, right buffer, and the input frame 1, which is our right hand stereo sample. So now we've written our samples in. So once again, remember there's no feedback in this model. So if we go back here, you can see we're not feeding back. We're not. If there was feedback involved, what we'd be doing would be taking some of this and then feeding it back there, like that. But we're not doing that in this particular design. So we're not doing that, which is at variance to the last example we did of a chorus unit where we did have feedback. In fact, it's if you use an analog chorusing unit, they don't have feedback. Only digital ones really introduce the idea of feedback for chorus. Okay, so when we read our sample, we've got our left delay sample, LDS, and our right delay sample, and they're coming out here. So as you see, we're going to split these off. We're going to pass a certain proportion of it through here into the summation units on either the left and right channels. But we're also going to take some of it and we're going to invert it and pass it into a high pass filter. So let's grab our inverted signal. So we have our left delayed sample. So we can say float left inverted sample. That's going to be equal to our left delayed sample multiplied by -1 delayed. And similarly, we're going to have our right inverted sample. And that's our right delayed sample. Okay, and we need to pass those now into our high pass filters. So we're going to have so we're going to cut off frequency. So we're going to set up our filters. So let's have another function which is going to be update. So this is a void function, update filter parameters. We're going to say auto. We only need to, because we're going to use the same cutoff frequency for both of the high pass filters. We only need to get the left hand param. So we'll just get params. That's going to be the left high pass filter dot get parameters. We can say params dot cutoff frequency is going to be equal to parameters dot cutoff frequency, and we need our algorithm. So parameters, so params dot algorithm is going to equal. So what's the algorithm? I think it was filter algorithm. Filter algorithm colon. So we want a high pass filter. So we've got several here. We've got some ones here. Butterworth single pole, dipole. Let's choose that one as our high pass filter. That's our algorithm, and the boost we'll leave the boost cut to be whatever it is on default. I believe it's going to be 0, and then we can say that left high pass filter dot set params is going to equal params, and we can also say that the right is going to use exactly the same parameters. So right high pass filter dot set params is going to be params. Okay, so we can do that operation at the same time. So we'll do that there, do it with every single frame, and do it during reset as well. So that sets up our filters. Okay, so we're going to pass our left inverted sample into our filter. So left filtered sample is going to equal our left high pass filter dot process audio sample, and then we pass the sample in, which is our left inverted sample. So just to remind you, over here in the diagram, we're passing our inverted samples in through a high pass filter, and they share the same cutoff frequency. So that's the same frequency. So the left goes to the left, the right goes to the right, and then we're going to feed that back. You can see it's going to go off to the opposite channel. Okay. Going to be interesting. I think we might need to have some kind of control on that. Okay, we'll figure it out. Because this has got, remember our signals here have got to always be between plus and minus 1. The normalized values of our samples, our floating point samples that are coming out here, have got to be between plus and minus 1. So we may need to do something to make sure that happens. Okay, so let's do the same for our right hand samples. The right filtered sample is our right high pass filter, our right inverted sample. Okay, so now we're pretty much ready to add things together. So we've got our wet dry mix that we need to sort out, don't we? So so this is the basic thing we need to change. Our output frame, left-hand channel. Let's just concentrate on the left-hand channel for now. Our left-hand channel is going to be whatever came in. So this is the dry signal multiplied by our wet dry mix left. So 1 minus that. So remember, we have this idea that they balance. So here, if this was 0.5, this would be 0.5. If this was 0.6, this would be 0.4. So they always add up to 1, which is why we're saying that A and B are those values. So A is going to equal 1 minus B. That means it always goes between 1. They kind of always add up to 1. Those two A and B values. So they're like a ratio of each other. So wet dry mix left. Okay, so let's just go back here. So we've got our left delayed signal multiplied by our wet dry ratio here. We got our unadulterated signal, but we need to feed in to the same summation, our mixer. We need to feed in the right hand filtered signal. This is where I think we're going to have a bit of a problem. So let's take this little lot out of the equation and call that left output sample. We're going to say that float left output sample is going to equal initially that, and we also need to add in our right filtered sample. So what worries me is if under the circumstances that might actually exceed the plus and minus 1 level. So we'll have to do something about that. Let's just grab this code and just do the right side. So right output signal is going to be that. Right delayed signal sample rather, and the left filtered sample. So that's the kind of crossover effect that we've got going on. This idea that we're taking the values and crossing them over. Some of the right hand channels being fed into the left. Remember this is the delayed samples as well. Okay, so what we're going to do about the fact that this could exceed 1, plus or minus. Let's just set this up. So one of the things that, just off the top of my head, one of the things that we did with the synthesizer project, which we wrote several streams ago now, which is the .NET Core 3 WPF N-Audio synthesizer, is we found a function which would help us. So let me show you that function. So we go over to our graphing calculator. If I give you this function, which is the hyperbolic tangent function, and if we look at this, the behavior of this function, you can see that between plus or minus 0.5, so between basically half and minus a half here, this is virtually a straight line. So we're getting kind of linear behavior. But as we start to get towards plus or minus 1, then this curve is approaching 1. It may appear to actually get to 1 here. In fact, it doesn't. That's an asymptote. So it gets infinitely close to 1, but never actually gets a value of 1. So this is one thing we could use to help us if we need it. We're going to start off without using it, and we're going to see what happens. But we've got this in our armory, in our back pocket, to try and kind of smooth out those values if we have a problem. Okay, so let's see if we compile. Yeah, hopefully we will. Yeah, we compile. Okay, well that's good news at least. So, over in our plugin processor, we can now declare an alpha dimensions chorus. we'll call dimensions chorus. Over in our plugin processor, we can go to our prepare to play, and we can reset our dimensions chorus with the sample rate. That's dot reset. Okay, so that's done the basics there, and we need to update the parameters. So let's define some parameters. We need more parameters. So we got rate and depth. Did we use depth? Yeah, we did. So there's the depth, and the rate determined the frequency of our LFO, which was there. We've got a couple of. All we need now is a cutoff frequency and the left and right wet dry mix values. So let's add a few more things in. So it means we're not using phase offset yet. We'll just drop that down and just forget about it for now. So we'll set up a new so wet dry mix left. So that's going to be a pointer. So we're going to use smart pointers in C++. So we're going to make a unique pointer. So these are pointers which are going to basically take care of themselves. We haven't got to worry about the memory management of our pointers and of the memory allocations that happen. So this is going to be of type audio parameter float. Like that, and we're going to give it a name of wet dry mix left. That's its ID, and its name is going to be left wet dry mix, and it's going to go between 0 and 1. And its default's going to be 0.25, let's say. So we can now copy that and have a right-hand version. Like that. Okay, and then the only thing we needed then was a cutoff frequency. So we can say auto cutoff frequency is going to be a standard make unique, and once again an audio parameter float. And this is going to be cutoff, and the name is going to be cutoff frequency, and it's going to go from 20.0, I don't know, 22,000.0, I don't know what it should be. We'll give it a guess of those values. And its default's going to be, we said 1,000, I think, within the plugin, within the class, so 1,000 hertz as its default value. So that should give us everything we need. Now we need to, what we're doing here is we're creating basically a vector which we're going to pass, a vector which is going to be passed back into this parameter layout type here. So we're returning it like this. So we need to set up a couple of these pushbacks, and we're using the move semantics here. Remember, we've got unique pointers here. We can't just copy them around. We've got to move them. Actually, these are called param at the end of them, so we'll do the same convention that I started there, param. So let's push these. Wet dry mix from the right, and our cutoff frequency. Okay, we'll just annotate that so we know that those are for those particular values are for the dimensions chorus. Okay. So in update parameters, which we call here, and which we also call for every frame that we process, every stereo frame, then we're going to need to set the parameters. So this is setting up for the delay, this is for the chorus stroke flanger, and we're going to do the same for our dimensions. So it's going to be, do they call it dimensions? Dimensions chorus dot get parameters. Oh, I didn't write a get or set parameter function for them. That's why that's not working. Okay, so we need a couple more public methods. We need get parameters. No, ahead. Thank you much for the follow. That's very kind of you to follow. So I hope you're kind of into kind of audio programming, because I've kind of got into it recently. So yeah, so this is all new stuff for me. So have some electric elf hype to celebrate your follow. I love the tentacle emote. That's wonderful. Very Cthulhu. So whose emotes that? Squid4 Twitch Global. Very nice. I like it. Okay. So where was I? On our public, we're going to need to have. So we're going to need to return that get parameters, and you can see how we're basically we're mirroring the features of these lower level objects. So our LFO is a get and set parameters, so our higher level object also is adhering to exactly the same interface, so we also need a get and set parameters. That's not the interface that's enforcing that, to be honest. It's actually a convention, but it's a good convention to follow. So this has got to be return parameters, and then we want a void set parameters, and that's going to take in params, and this is where we get to use our overloaded assignment operator. We can say parameters equals params. So that makes overloading the assignment operator up here means that's really simple. Okay, so this is our overload of the assignment operator within this struct. So it means that we can just do an equals, and then that's our getting sets are really kind of simple. Okay, so now we've got that, we can actually go over here and get parameters here. So it's our params, and then we want to say that dimensions params dot cutoff frequency is going to equal to our, we need to dereference our plugin state. So if you're new to JUCE, we're using some of the features of the JUCE framework here to control our audio parameters. And what I've done, just as a quick diversion, I've set up something called plugin state here, and this is of type audio processor value tree state. This is a built-in class that comes with the JUCE framework, and it enables really to as a place to store our parameters, and also enables us to interact with the GUI in a neat and simple way, which is very useful for us. And also not only with our GUI, but also with the GUI of any host. So, for example, if you're using this plugin within a DAW, I use Reaper, then we can hook in to these parameters from our DAW and control them from there and automate them within the DAW as well. So it's not just as if we've got GUI control, we've actually got automation control by using this audio processor value tree state structure. Okay, so we need to get the raw parameter value like that, and it's going to be the what did I say, cutoff, because that's the ID I gave it. I believe that was the ID I gave it anyway. Let's just make sure. So I called it cutoff there. So we need these ones as well. So dimensions. Dimensions params dot depth. Well, that's going to be the same as that one there. We'll grab that code. And we can just grab it again. It's going to be our rate, and that's going to be rate. Oops, I think I've got I had me. I just hit the insert key on the keyboard. And then we've got the left and right wet dry mixes. So dimension params dot wet dry mix left, dereference our plugin state. So at this stage, my kind of knowledge of C++ is still quite low, but I'm able now to kind of leverage my C# skills to actually get to grips with some of this. So this is simple left-right boilerplate code. So there's no skill required here, no knowledge of C++ necessarily, apart from the fact you need to dereference your plugin state, because that's a pointer. Okay. This was get raw parameter value, and this was going to be wet dry mix left. Just to save my typing, I will grab that and repeat it, and this will do the right hand side. Hope after all this that it actually sounds any good, because I don't know what it's going to sound like. And then we want to do dimensions chorus dot set parameters, and we want to pass into their dimensions params. That should configure our parameters. We could actually comment out these lines of code, but I'm going to leave them in, because if it starts to cause any glitches in the audio, we'll comment them out, but I'll leave them uncommented for now. Okay, and down here, when we do our processing, we actually want to use our dimension chorus. So now, because we've built the classes off in our header file, our codebase alpha fx header file, our process block where we do all the kind of work is now very, very simple. All we do is pulling out the frames, the left and right channels into a frame, and then just feeding that into our class and invoking process audio frame on it, and then the output, set the sample outputs like this. So it's really, really simple. Whereas before we had an awful lot of code in here and it started to get very, very messy. So that's our process. So we still can't, let's make sure it can build, but we can't actually try it out yet because we haven't got a GUI which will allow us to feed these values in. So we now need to do some work in our plugin editor, which is where all our GUI controls are. So this is where all that happens. So what we should be able to do is set these basic things up. So we're going to need 3 sliders. We need sliders for wet dry mix left, wet dry mix right, and cutoff frequency. So let's produce those here. So slider is a built-in JUCE class. So there's lots of really helpful GUI bits and pieces that come with JUCE. You can write complete cross-platform GUI front ends for desktop applications or whatever. But we're using JUCE for audio plugins really. But say JUCE is extremely kind of versatile. It doesn't just do audio plugins. It'll do audio applications. It'll do desktop apps. It'll do console apps. But it gives you a whole load of really, really useful library code, so that you can work with higher level building blocks. You're not writing everything from scratch. So in that sense, it's a bit more like a kind of a .NET framework library, and it's giving you lots of classes to help you out. So this is going to be our wet dry mix left slider. Onto the slider. Wet dry mix right slider, and another slider which is going to be our cutoff slider. So there's 3 additional sliders we need for our dimensions chorus, and we can reuse these ones here, the rate and depth. So that's the definition of them. We're also going to need some values, and that's what these things are. So the thing that's using the audio processor tree state gives us is access to this thing called slider attachment. And what slider attachment is doing is basically it's creating a listener. So rather than using the observer pattern, the listener kind of listener and subscriber kind of model, which you would use if you were building a GUI app for the desktop, for example, in which case you would implement the observer pattern and have a listener and all that. What we get with this audio processor value tree state is these attachments, and basically this is making that link for us. It's creating that link between when you set the slider, it's automatically feeding those values back into those audio parameters we defined in the plugin processor. So it kind of takes a lot of the kind of heavy lifting away from you. You haven't got to write a lot of boilerplate code. There's plenty of boilerplate code you have to write with JUCE, but this one kind of takes that away. It does initially look a bit complicated, but actually it turns out that it's really quite useful. All you do is once you've got one of these things written, it's a matter of copying code. Okay, so we've got our we can just copy some of these down. Let's grab this one. This is going to be so these are called value at the end, so that's going to be the left value, the actual value that the slider is set to. So we create a right hand attachment, and we're going to actually wire these up to the various sliders in the next step, and then we've got a slider attachment for cutoff frequency. Okay, so that's the basic variables that we've declared. We've got our sliders declared. Those 5 sliders there are what we need, and we've got our 5 attachments. We're not going to be using these attachments or those sliders at all in this particular plugin. And what we're doing at the moment is I'm kind of using the same piece of code to kind of test all kinds of different algorithms. Kieran, thank you very much for the follow. I'll guess Kieran. It sounds a bit Celtic. So have some electric Alf hype for your follows. Thank you so much. That is really, really kind of you to follow. I really do appreciate that. I know. See, I'm really kind of appreciative that we've got a few people watching the stream, because I know I'm up against some people who, some big streamers at the moment. So normally I stream on a Monday and a Wednesday, but because I'm on holiday from work at the moment, I'm having to kind of juggle my schedule. So this is an unscheduled stream, which is clashing with other people who are much more well known as streamers than I am. So that's why I'm so kind of pleased that I've got some people watching, because I didn't expect anyone, to be honest with you. Okay, so that's our values. Let's go over to the plugin editor code. Okay, this is what creates our GUI, and what we're going to do is we're going to copy some of this. We're going to copy some of this, and we're going to comment some of this out. So I think what we'll do. What should we copy? Let's comment out that code, which is the phase offset. We'll leave the rate and depth. We'll comment out delay, feedback, and the wet dry mix. Comment that out as well. So we've got a rotary slider for rate. This is the low frequency oscillator rate in hertz. And we've got our depth. This is our oscillator depth. So what we need is wet dry ratio left and right. So we can copy this code, and we'll just use that. So what I did in an earlier stream, I created this helper function called make rotary slider, which is really just to help us out, so we don't have to have so much repeated code. So that's our left. And so we need some labels as well. So this is one of the kind of things you have to get used to with working with C++, is having to define things in more than one place. So let's create some labels. So what we'll do is just separate these out like we did before. So left dry mix left, wet dry mix right label, and cutoff frequency label. Cutoff frec label. Okay, so those are the labels which are going to appear underneath our controls. Wet dry mix left label. This is where we need to remember to left and right after everything. So that's our left wet dry mix, and we need to join that up to wet dry mix left, and it's wet dry mix left slider, the value. So this is hi there, Nana, you got a question? Oh, thanks for the kind words. I'm glad you find it interesting. So I started off with doing a lot of .NET stuff, and I wrote I think it's 4 or 5 streams ago. I kind of wrapped up initial work on a synthesizer which I wrote in .NET Core 3 and WPF, and to do when I was doing that, I was creating effects for it, and I got quite interested into the kind of the signal processing behind it, and which is why I've kind of decided to do some streams on JUCE and some DSP kind of plugins, because I do find it quite fascinating to be honest. It's very interesting stuff, and I didn't know if anyone else would find it interesting, but I'm glad you're interested. It's encouraging. Remind you of one of your uni group projects, a lot more sophisticated. Well, is it Kieran? Yeah, I hope it is, because that's so yeah, I think Kieran, good, I'm glad. So you say you guess had a decent amount of audio knowledge. That's not true. I didn't have any audio knowledge, so this is all kind of book reading, research, playing with code. And the reason why I want to do this is because I don't know what any of these effects actually sound like. So I want to play with them. So if we can build them in software, we can then start adding new features. We can start changing ratios. We can kind of add new controls. In this particular plugin that we're building, this feed here of when we take in we take a feed off of the right hand channel, inverting it, passing it through a high pass filter, and then feeding it into the left hand channel. We don't have any kind of gain control here, but we could actually create one now and see what it does. So no, you're lost. I'm sorry that you're lost. Do ask any questions and I'll attempt to answer them. But some of this is kind of, some of the stuff I'm doing now is like JUCE ceremony. So it's kind of how you set up a GUI in JUCE, and it's not really, it's just something you have to pick up. And I must admit, I'm not great at it, but I'm kind of slowly learning. Okay, let's set up our right hand wet dry mix sliders. So right there, this is going to be right. I sometimes wish you could actually that it would actually oh, there's a mistake there. That's going to be a left look. That you could encapsulate this in a better way, and I think I probably will be able to. It's to kind of pull this kind of GUI stuff out into a class, but I haven't kind of sat down and thought about it enough yet to do it. Ultimate digital guitar pedal, yeah. So I do play a bit of guitar, and I've got a whole bunch of guitar pedals on the floor there. And yeah, because I've got a DAW, I could actually plug my guitar through that DAW and actually use my own digital effects. So if I want to create decent ones, I've got quids in there, really, aren't I? So I'll be able to use my own, which will be quite interesting. So that's right. This needs to be right. And then this line here, this make unique. This is where we're creating the attachment. So we're linking up with the plugin state, which is defined on the audio processor side over here, and this is the identifier of the audio processor value tree state parameter, and this is the slider that we're associating with it. So this line here is basically doing that. Whenever you move the slider, feed the value of the slider through over to the processor side so it can update stuff. So Kieran, our project was a guitar pedal. Oh right, so you actually okay, that's wonderful. So you actually did a hardware guitar pedal. That's really interesting. Oh, I'd love to have done electronics. I didn't, unfortunately. I did chemistry at university, so yeah. But I would have loved to do electronics. This needs to be the right hand label. So it is all the kind of ceremony, not particularly interesting stuff. And then the right label. What did I do here? Wet dry mix right label. What's wrong with that? Dry mix right. I misspelled it over here. There we go. Fixed. And the other thing was the cutoff frequency, wasn't it? So let's add that. Let's add it at the bottom. No, we'll add it after the wet dry mix. This is going to be our cutoff frequency slider. So cutoff frequency value is going to equal this little lot over here. We're linking up with a cutoff parameter defined on the processor side. This is the cutoff frequency slider. Well, okay, so right, I see. So you're familiar with Javid X9, you guys. So yeah, he's great, isn't he? I really do like his streams. Cutoff frequency slider, and then we've got cutoff frequency label. I just called it cutoff with a lowercase o, didn't I? Yeah, so this is, once again, it's the kind of ceremony of JUCE GUIs. I'm sure we can do something to refactor this into a much nicer way of working. But so what we're setting up is the rotary slider there and the label that goes with it. Okay, so we've got five variables. We've got left mix, right mix, cutoff frequency, rate, and depth for our LFO. So now we need to go over to our GUI kind of layout. And what I've got here is I've got 1, 2, 3, 4, 5 rows. The first row contains the name of the plugin, like a heading. Then we've got a double height row which contains the slider and the label underneath that, and then another row, another label, and then we've got 3 columns. Okay, so that can stay the same. So we're going to have in here, so let's do some commenting out. So let's comment out that line, that line, that line, that line, that line, and that line. Okay, and we don't need a phase offset. So we've got our rate and our depth. So let's now just pop into here, a new grid item. So I'm using grid layouts. You can use Flexibox layout as well, which is very similar to kind of CSS, if you're familiar with that. You've never met Javid in real life? Maybe just more popular thing? Yeah, possibly. Okay, so let's fill in here. We need to have our wet dry mix left slider, grid item, wet dry mix right slider, and our grid item cutoff frequency slider. So those are those. Then underneath each of those, we're going to want to have their respective labels. So another grid item. This is a bit of a pain, all this kind of ceremony to set up your GUI, but there may be better ways of doing it. So the wet dry mix left label, item wet dry mix right label, and grid item for the cutoff frequency label. Right. Will it build now? Looks like it's going to build. Yeah. Okay, let's just eyeball the code once more. So we've set up our in the constructor here with our editor, we've set up the size of our canvas. We've got a heading, and we've got 5 sliders and 5 associated labels. And then in our resize method, we've created a grid. It's 5 rows, 1 row. We're only going to fill in 5 sliders and 5 labels, and then we perform the layout. And this is the helper function I wrote. So make rotary sliders that I wrote. So I think we can possibly start to build maybe a little GUI library to kind of remove some of this kind of left-hand, right-hand boilerplate code. I'm not sure what to do with it yet. Okay, so let's fire it up. So here's our so it's all a bit messed up, so we're going to need to do some. Okay. Okay, let's sort out what the grid looks like. So it's a it's got that many rows, and it's 3 and 3. So I think we need to bring these 3 items up underneath here. So we've got 3 columns. So 3, 3, and then 2 and 2. So that should take care of it. And we'll need to build. Oh, it's going to build for me. I'm going to build it again just in case, because I've fallen foul of that before, it not actually really building, and no changes being reflected in my GUI. Okay, come on, it's built. Let's debug. Okay, so let's have a look, see if that's kind of better. That's for some reason sitting under there. I need another grid item in there, don't I? So let's sort that out, because it's annoying not to have a nice looking GUI. So if I put grid item with nothing in it, I wonder what it's going to do. Hopefully it'll let me do that. Just like a placeholder. Let's try that. Yep, there we go. So we've got our 5 controls. So let's just put our wet dry mixes down to 0, our rate to 0, depth to 0, our cutoff frequency to cutoff frequency. What should that really be? I don't know. I have no idea. Let's put it. Put it up somewhere in the middle. Okay. Let's get an audio player going. We'll open our royalty-free track. Play it. So can you hear that in chat? Okay, so let's start playing around with this. So let's up our rate to another depth of 0.1. I'm not sure I can hear anything going on. Oh, so there's an effect. Okay, I can't hear anything. That's the problem with this. So let's look with an oscilloscope. Let's stop that. Let's move all these things around a bit. Disconnect the audio player. We'll put in a synth. Connect up these bits and pieces. I'll disconnect those. Come on, disconnect please. I'll start again. Okay. That into there, that into there. Let's get an oscilloscope into the picture. Plug those in. We'll have a look at a oscilloscope. I'll just hit a key on my MIDI keyboard. So we need to have the time lowered. The waveforms, I can see what's happening. Let's just let's put feed some of this in. I can't hear anything happening. So I don't think there's anything happening there at all. So let's go and have a look at our code and see what could possibly be wrong. So there's something not quite right. Okay, so we've got these controls presumably are being processed. Let's go over to our plugin processor. Okay, let's drop a breakpoint. We're going to drop a breakpoint in there, I think. Put it in there. Bring it up. Okay. So we're going to get the parameters. Our parameters are left and right mix at 0.25, rate of 1 hertz. Okay. Cutoff frequency of 1000 hertz and a depth of 5, and then we're going to go and change those. So that's now going to be 1000. Yep, that's 25. I think these are the same values. And we set output. Okay. Let's just continue. Remove that. Continue. Okay. So now we're going to just drop a breakpoint in here. I'm going to play a note. Oh, so we need to. Let's just load in a sound file and play it in. And then we're just going to drop a waypoint in there, and we'll step into that. There we go. So we should have updated our parameters. It's interesting that's 1, isn't it? I'm interested. It's 1. It seems unlikely that it would be 1 at that point. Let's step in again. It should have changed. 1 hertz. Triangle wave. Still 1. To remove that and continue for a bit. Definitely no effect. I can't hear anything happening. Okay, let's have that. Drop a plug-in, put a breakpoint into there. Step in. Oops, I've stepped over. Continue. Step in. Still plus or minus 1. Which is why it's having no effect. It's not oscillating. It seems inconceivable that it would always be 1. So what is going wrong with our LFO? So that's correct frequency. Step over. Frequency is now that. Yeah, that is exactly 1, which is not correct. Okay. Something weird going on. Okay. So this is where we have to go and compare this code with what we had from the working versions, which was up here. So we render the output. That looks correct. LFO output. Normal output. So why isn't it oscillating? Staying at a constant level. Try with a cutoff frequency of 100 Hz. Okay, we can try that. We need this to be logarithmic. Let's put that rate up. I just can't hear a chorus effect at all, which is alarming. So it's definitely dropping through here. We're not running into this thing where the input sample is exactly the same as the output sample. A shared LFO, render audio output. That's producing a struct. And we've got normal output and inverted output. Stop it. What's the best way of trying to figure this out? Let's play it again. So the delay sample is always 0. Oh, that one isn't, is it? 1.75. So those are producing values, but those are not, that's not fluctuating, which is why we're not getting any kind of chorusing. We should be getting an echo, I would have thought, but so left delay sample is being inverted correctly. Oops, didn't want to do that. The input frames being written correctly. Read buffer. What's our filters? We're getting samples out. A left output sample. It looks okay apart from the fact that that is not oscillating. Why is that not oscillating? Always the same values. Let's go and compare it with the code up here. Okay, so We do the same kind of thing. We just render the output on every quarter sample. Render the left LFO, render the right LFO, do the cast to float, work out the delay in samples. No, thank you for joining us. That's really kind of you to join. So thank you so much, and maybe we'll see you again. And thank you for the good wishes. Dragon Eye, hi, good to see you. And this is really strange. Our oscillator is not oscillating. So let's go down here. We've got a shared LFO. Left. Oh, look at that. That's the reason. We're not doing a set parameters on it. So shared LFO dot set parameters. I think I forgot that last time as well. Let's build. So that's why it's not varying. It's just producing basically DC. Dear me. Okay, let's try again. Well, we've hit a breakpoint. Let's lose that. Okay. Let's try again. So open up our test track. So there's an effect now, isn't there? Like a shimmering effect on that. Okay, well let's pop a oscilloscope in there and see if we can see it actually affecting the waveform. So we'll put that over there. We'll get a sine wave generator in. Pop that into there. Get an oscilloscope. Put those in there. Oh, look at that. Slow it down a bit. Okay, let's see if we can get a decent signal. We need to increase the amplitude. Okay. Right, let's see if we can get any effect going on. Oh, there we go. We are getting an effect. I don't know if you can hear it. It's a very subtle effect. Cut-off frequency of the filter is... I'm not sure what that's doing for us. We need to have a fair amount of wet mix in there. And we get the effect. Interesting. Okay. So it is working. Whether it's a particularly impressive chorusing effect, I'm not quite so sure. You can hear it definitely there. You can see it on the wave on the oscilloscope. We're getting that effect. It did say it was quite subtle and transparent, but it looks like you need to have mix a fair amount of stuff in. Let's put much more in. Okay, well, it's certainly working. Whether we can notice it particularly with the track is what I'm interested in. We need to pile up the wet dry mix. Yeah, there you go. I'm not sure the cutoff frequency does an awful lot for me. Oh well. We now know what a Roland Dimensions chorus unit kind of sounds like. As long as I've coded it right, it looks okay. That's what it sounds like. Certainly very different from how the other chorus unit, the very simple chorus that we wrote, sounds. I'm just going to turn up the volume briefly on the So I'm wondering if we're going over the one of the problems that I thought we might have was actually having signals which were over outside the range of plus and minus 1. So let's have a look at that. What we talked about doing was introducing hyperbolic tan to smooth out, so we don't actually get above plus 1 or below minus 1. So let's try. This is quite. The problem with doing this is it's a bit kind of expensive in terms of. I wonder about what we've got here. This is the problem. This should be plus, not multiplied by. Because we're mixing the input with the output. So let's try it with that, because that's going to make a big difference. So bad code. We'll soon find out, but I think that's why we're having such a subtle effect, is it's not actually doing what we expect. But the other thing I'm worried about is these going outside the bands of plus and minus 1. So we'll see what happened. Did that succeed? Let's try again. So we weren't mixing. Yeah, idiot. Yeah, should have seen that. Okay, let's try again. Audio player. Now we're getting some chorusing. Well, that's better, isn't it? We want to keep the rate low. That's better. I was expecting something more dramatic. It was extremely subtle before because it was multiplying rather than adding. That's better. Okay, so see what we got the high pass filter in there because we get a lot of weirdness going on. We can tidy that up a bit with by putting just letting the higher frequencies through. That's nice. So it sounds, it detunes a bit, but it's sounding quite orchestral, as if there's lots of violinists or whatever going there. And then we start getting the pulsing, which is quite fun. Shimmering. Ooh. Yeah, quite a lot of detuning going on. I think it needs a fairly low rate. That's really, really quite nice, isn't it? Yeah. And the high pass frequency, the high pass filter lets us kind of clear some of the distortions out, doesn't it? Okay, that's good. So that's this, the a Roland Dimensions style chorus unit. So I'm quite happy with that. That's worked out quite well. And once we got the code right. So it looks like we're actually kind of starting to build up a few, pardon me, interesting sounds. So we've got our simple delay, and what I'd like to do in the next stream is to actually build a multi-tap delay. Thank you, DragonEye. It does work pretty good. I'm pretty pleased. Look at this, a Gameforce Ready drivers available. I don't think I'm going to be installing that now. Go away for a bit. Okay. We've got our chorus stroke flanger, which sounds okay. The flanger sounds pretty good. And then we've got a dimension style chorus. So that's kind of a classic effect recreated. So that seems to me like a good point which to finish. So thank you for those people who've stuck with me. It's been a lot of fun. I'm glad that we actually got to the bottom of why we're getting a very, very subtle and weird effect. Just a plus sign rather than a minus sign. And still a bit worried about these values. Shall we try applying a shall we try the tan, hyperbolic tan? Have we got hyperbolic tan available to us? Look what we have. Let's just try it and see if it has any effect, good or bad. Let's build that. So it might be a bad effect. In which case we'll remove it. Okay, same track. Low rate is what we want, isn't it? Probably don't need it, do we? Not detecting any. Maybe just distorting the sound even more. Yeah, let's remove those hyperbolic tan functions and then just try it once more without them. But I don't think we actually need them. At least not that I can tell. Obviously, looking at this calculation here could yield values greater than 1. Yeah. Try it once more, and let's try a different piece of music, Part of Life. Yeah, I don't think we need that tan function particularly. The low rates is what we want, I think. Simply changes the sound of the track. Yeah, no, that'll be fine. Okay, well that's I think we'll call it a day. So what's the time? 10, so I've been going for about 2.5 hours. Is that right? I think that's enough. Okay, so let's just commit those changes. This is a Roland Dimensions style chorus. Spelled chorus correctly. And we'll sync that up to GitHub. So if you want to have a look at the code or play with it, it's all up there. Thank you, DragonEye. Appreciate you being in chat. It's great to have you there. Okay, so let's go and find someone to raid, shall we? I think Gareth Hubble should be streaming, so let's go and raid Gareth. So we want Twitch. Yes, there's Gareth. We're going to raid Gareth Hubble, who's doing C++ as well. I believe he's working on his bot. So do stay with me to join that raid and spam chat with emotes. Take care, DragonEye, and we'll see you next time. Let's raid. And here we go. Take care, everyone.